Hello students, welcome to Vista's Learning. This is Shruti, your chemistry tutor. We are in 11th standard chemistry and we Vista's Learning provide you the quality education for all. As we know, we are in the S block elements and we know this is the 5th lecturing class. If you have missed any of the lecturing classes, you can browse into our web application www.v-learning.in. So this is the S block elements which we have already started studying about them. We'll go ahead with the general characteristics of some of the compounds based on second group. Second group are also called as alkaline earth metals, right? So what are the first characteristics which go ahead with this? Di positive. What do you mean by di? Di means two. Positive means which can lose 2 electrons and become positively charged particles. So here these alkaline earth metals will lose 2 electrons and become di-positive. So their oxidation state will be +2. Their oxidation state will be +2, and this is a predominant valency of group 2 elements. If we take the periodic table, generally first group elements will have oxidation state as +1, second group will have +2, right? Third group will have +3. It goes on like that. So the next one is ionic nature. Are they more ionic than alkali metals? As we have already studied, alkali metals are very strong oxidizing agent or reducing agent. They are the reducing agent because they lose electrons and make the others oxidized. So they are the oxidizing agents. If you see the ionic nature, these alkali metals, even though they have +1 charge and alkaline earth metals have +2 charge, but the ionic nature will be very strong for alkali metals, that is +1 charge than that of +2 charge. Got it? So here these alkaline earth metals are less ionic than that of corresponding alkali metals. So why this is? Because as we know, this is due to the increased nuclear charge and smaller size of the alkaline earth metal. As we go from left to right, what happens? The size decreases. As the size decreases, alkali metals can easily lose the electrons, whereas alkaline earth metals cannot. And there we have the nuclear charge which is exactly acting on the outermost orbit, and it will be more attractive than that of alkali metals. And smaller size makes the electron to be held with the nucleus. So alkali metals are more stronger or more ionic than alkaline earth metals. But compared to other elements of the group or the periodic table, if we see, the alkaline earth metals are ionic in nature or more ionic compared to other periodic table elements. The oxides and other compounds of beryllium and magnesium, if we consider, we know that whenever we take the group, the first element of the group will always be smaller, because down the group size increases. As down the group size increases, and if this first element is smaller in size, that will have the different character. It is just differs in some of the manner, and it is not exactly having all the properties what the complete group will be exhibiting. So here beryllium and magnesium are more covalent than that of the other larger members. We know that beryllium and magnesium are smaller in size, whereas calcium, strontium, barium, when we go down, they get larger. So what happens? These are larger size and they have larger size and they will become more ionic than that of beryllium and magnesium, where beryllium and magnesium partially they show covalent nature than the other elements. Covalent nature means sharing of electrons. Next, oxides and hydroxides of second group elements, that is alkaline earth metals. So these burn in oxide, like oxygen. If you have the oxygen in presence of oxygen, what happens? They burn to give monoxide, MO, monoxide. If you take M as a alkaline earth metal, as we know, M will be having +2 charge, O will be having -2 charge, and if we crisscross and cancel them, we'll get MO. So this is called as a monoxide. They form monoxide, where we find that the first group elements will find dioxide or peroxide or superoxides. So these monoxides of alkaline earth metals are found as rock salt structures. They will be having the structure as rock salt. I have shown you how does the rock salt will be having. It will be cuboidal in shape, right? So here the sodium, and in the corners you will be having chloride ions. This is how the structure of rock salt will be. We will study in detail in solid state in 2nd PUC or 12th standard. So here, except this beryllium oxide, all other group members will have the monoxide, and that will be having the structure of rock salt. Beryllium oxide, if we see, they are covalent in nature. Since it is not ionic in nature, sodium chloride is a rock salt, right? This is a good ionic, strong ionic compound which we know. So they are been having the same structure of monooxide of alkaline earth metals. If you see beryllium oxide, it is covalent in nature, right? So it cannot form the rock salt structure which is ionic in nature. This is amphoteric, while other oxides are ionic in nature, right? So amphoteric means what? It acts both as acidic and basic, then we call it as amphoteric. All these oxides except beryllium, we need to consider this, because in first group element what happened? We studied about lithium, right? Lithium is separate from the other elements. Likewise here the next group element, second group element, the first element is beryllium, which will be having a bit different properties than that of other group elements, other elements of the same group. Why? Because just because of its nuclear charge, attraction between the nucleus and the outermost orbit, and also the size. The size is very small, and that makes the difference in the character. And these oxides except beryllium oxide are basic in nature and react with water to form sparingly soluble hydroxide. What is the sparingly soluble? Means partially soluble. They are not directly soluble like NaCl. If you take and add it, what happens? You will get it will dissolve completely, but these oxides will not dissolve completely. They dissolve partially. That is called as sparingly soluble, and that hydroxide will be formed. When oxides reacts with water, they form hydroxide. If I take magnesium oxide reacting with water molecule, we get magnesium hydroxide. Okay. We can see the general equation. The monoxide of alkaline earth metal reacts with water to give the MOH twice. You can take any element rather than beryllium of alkaline earth metals. Next, solubility. How they are soluble? I just said the hydroxide, if we add monoxides into the water, they are sparingly soluble, right? So we'll just study about this. What happens to the solubility? The thermally stable and the basic character of these hydroxides increases with increase in atomic number. That means down the group, it increases with the solubility. Why? Because as they go down, the ionic nature increases. As ionic nature increases, they dissolve easily. From magnesium hydroxide to barium hydroxide, if you consider, that is magnesium. They are not considering about the barium. You need to concentrate on that. Barium will not be considered. From magnesium to barium, if you see down the group, the size increases. That means, see here two things will be there. One, the size increases they can give, or increasing atomic number. There are two chances. The atomic number increases left to right and top to bottom. Right, but when they say in the same group, when they are specifying the group, how does the atomic number increases? It increases downwards itself, right? So what happens? From magnesium to barium, the size increases. As the size increases, ionic nature increases, and hence the solubility increases. Thermal stability will also increases. What do you mean by thermal stability? Thermal means heat energy. Stability means to withstand, right? If we speak about thermal, that means even though I am giving the heat energy, that will not loses its stability. So if you take ionic substances, they are positive. For example, I'll just take Na plus and Cl minus. As we know, it is a very strong ionic substance. So if you give heat energy, they will not easily separate. They require more heat energy to get separated because they have a bond. Bond means agreement that I have given you the electron, you have taken my electron, and we need to be together. That is the agreement between sodium and chlorine. If they have to get separated, either sodium completely loses electron and chlorine will completely gain the electron, and they need to separate. That is not so easy. And also, if they are positive charge and negative charge, they are not so stable. Then they'll get attracted with the oppositely charged particles. So they come closer and they become very tightly packed substances. It is not so easy to separate positive charge and negative charge. So you require more energy. So what we say, whenever we say the ionic compounds are there, they will be having more thermal stability. If I speak about other things, like if I have carbon with the hydrogen, methane. I'm just giving an example of covalent bond, okay? Here they are just sharing. I have one electron, I'll give one electron, you also give me one electron, we'll share it. The bond between them, the agreement between them is that, okay, we are sharing. If I don't like this hydrogen, I need to remove that hydrogen. If some other, like chlorine is there, who is very strong, he is also saying that I'll also give one electron, you can come and combine with me. So what happens, this carbon can easily break this bond and combine with this, right, such that hydrogen can easily come out. For this bond to break, we require very less amount of energy. So covalent compounds can be easily broken with heat energy. So we say for covalent compounds, thermal stability is less compared to that of ionic substance. Hope you understand this. So what happens? Stability and solubility, also basic character increases down the group as the atomic number increases from magnesium to barium hydroxide. Alkaline earth metal hydroxides are less basic and less stable than that of alkali metal hydroxide. That is obvious. See here, these are basic in nature. That is the first thing what we need to know. But they, if we compare it to alkali metals, always we need to compare with the other elements, right? So first group element, if I take, this is the second group element. So first group and second group, if I take, what happens here? The first group hydroxides are more basic. They are more basic because they are more ionic in nature. And also if you take the second group elements compared to that of first group elements, the second group elements are less strong in basicity, or they are less basic in nature. Beryllium hydroxide is amphoteric. As I said, it acts as both the base as well as acidic in nature. So as we know, it reacts with acid as a base, and it also reacts with alkali as an acid. So it is called as amphoteric in nature. What do you mean by amphoteric? Which acts as both acid and base. Remember, if amphoteric is been given, it can react with acid as well as base. So beryllium hydroxide, when we have the basic in nature, what happens? It again forms the berylliate ion. Whereas if you are taking the HCl is a acid. When beryllium hydroxide is reacting with acid, what we get? We get a complex. Getting good. Next we'll go ahead with halides. What do you mean by halide? As we know, halides comes for halogen. When these metals react with halogen, we get halides. So except beryllium halides, all other halides of alkaline earth metals are ionic in nature, because these second group elements are more electropositive and 17th group element, that is halogens, are more electronegative. When there is a difference in electropositivity and negativity, obviously they get attracted towards each other and form ionic character. As we know, beryllium will be having smaller size, it cannot easily give out the electrons and it will not form the ionic compound. Beryllium halides are essentially covalent and soluble in organic solvents. I have told you this. When we have polar molecules, they dissolve in polar solvents. If you have the covalent bonded substances, they dissolve in covalent solvents. So organic solvents, organic means what? These are the substances which contain carbon and its compounds. So carbon is a substance which is having 4 bonds. Generally it will be always covalent. So organic substances are generally covalent in nature. So covalent compound will dissolve in covalent solvents. Coming back with the vapor phase of beryllium chloride, it tends to form chloro bridge. What is this chloro bridge? We'll study that. Dimer means you'll be having BCl3. It is a beryllium, right? BeCl2, because Be will be second group, so +2, Cl will be -1. When we crisscross, what happens? Be1 will come here, Cl2 will go there. So we'll be having BeCl2 as a formula for beryllium chloride. So this forms the bridge or dimer. What is that dimer? If we have like this, one more molecule will have the connection with the other one. They form the partial bonds that we'll study. Okay, that is called as dimer. Di means 2, mer means units. 2 units combining together to form one bridge, like they are forming the chloro bridge, and that we can call it as a dimer. Okay, that will be associated with the linear monomer at high temperatures, like we can easily give 1200 Kelvin to form this. You can see here the structure where beryllium chloride is being formed, and this is the attraction, what it will be, the exact attraction between the other chloride ions. So here this forms the bridge between 2 beryllium atoms. So if I consider this is one molecule, BeCl, and this is one molecule, and this is another molecule. So how many molecules are there? 3 molecules. It is just a chain, like we can consider only 2 of them. Okay, this beryllium will be having this chlorine, but this chlorine will get attracted with the other beryllium which is adjacent to it, and the chlorine, what it is having, again that will be having the attraction with the other beryllium. This will be forming as a chloro bridge in beryllium chloride. So tendency to form halide hydrides generally decreases down the group. What do you mean by halide hydrides? So if you take here, we have this salt, magnesium chloride salt, and when it is been mixed with water, they form hydrated salts, right? So these alkaline earth metals halides will have the hydrated salts, but that decreases down the group. As we see, for magnesium we can have 8, that is octahydrated, whereas for calcium it is 6 hexahydrated. Strontium we have 6, whereas beryllium we have only 2 water molecules which is accompanying the halide of barium. Got this? So what happens down the group? This hydrated water molecules will get decreases as the size increases. So dehydration means, D means to remove, hydration means the water molecules which is present. to remove the water molecules from these hydrated salts, you can say hydrated chlorides, bromides or hydrides of calcium, barium and strontium can be easily done by just heating it. It is just, as we know, calcium, strontium and barium has the higher radius down the group. What happens if you just give the heat energy, these water molecules can be removed. That removal of water molecules on heating, you can also call it as dehydration. The corresponding hydrated halides of beryllium and magnesium, if you see, they can suffer hydrolysis. They cannot easily remove the water molecules, but instead they undergo hydrolysis. So fluorides are reactively less soluble than that of chlorides. As we see, the lattice energy is more and we require more energy to break this fluorides, because fluorine is a very highly electronegative element. It will be bound very strongly. It is not so easy to separate the fluorides. So as we know, it is having high lattice energy, so it is not easily soluble in the water or substances. What happens? Chlorides, bromides, iodides, they can easily dissolve. Next, salts of oxoacids. What do you mean by oxoacids? If the acid, if I take hydrogen, oxygen, so this is the OH group which they are containing, and if it is connected with the sulfur, what happens here? We have like this, right? This is oxo thing, where this oxygen is also combined with the central element which is having the H with it, where it can easily remove the H plus and become the acid. Got it? So such salts of oxoacids, if the oxoacid is reacting with these alkaline metals, what do we get? These forms the salts of oxoacids will just go with the carbonates first. Carbonates of alkaline earth metals are insoluble in water. They are not soluble in water as they precipitate by addition of sodium or ammonium carbonate solution. This solubility of carbonates will decrease as the atomic number of the metal ion increases. That means down the group solubility decreases. All the carbonates decompose on heating to give carbon dioxide and their oxides. As we know, calcium carbonate, if I take, when they subject it for heating, we get calcium oxide plus carbon dioxide which has been liberated out, right? So this is the character of this carbonates of alkaline earth metals. They can easily remove the carbon dioxide on decomposition and gives its oxide. Next we have beryllium carbonate is unstable. This can be kept in the atmosphere of carbon dioxide. That means they are not stable easily, and the thermal stability increases with increase in cationic size. Down the group thermal stability increases. I have already informed you about that, right? Next, coming with the sulfates. Carbonates we finished. What about the sulfates? Sulfates of alkaline earth metals are all white color solids and they are stable to heat. That means if you give the heat energy also, they are stable. They doesn't decompose. They don't decompose. So beryllium sulfate, magnesium sulfate are readily soluble in water, whereas the solubility decreases from calcium to barium. As we said, these are very strong as they doesn't easily dissolve in water. So down the group what happens? Solubility decreases. The greater hydration enthalpy of beryllium and magnesium ions can easily be overcome by lattice enthalpy factor. If you give the heat energy for them, they can easily overcome that greater hydration enthalpy. Next we have this nitration. What is this nitrates? As we know, the carbonates will have CO3 minus 2, sulfates SO4 minus 2, and these nitrates are NO3 minus. So salts of these oxoacids, these all will form acids: nitric acid, sulfuric acid, carbonic acid, and when these metals are reacting with all these oxoacids, we get these salts of carbonates, sulfates and nitrates. So the nitrates are made by dissolution of carbonates in dilute nitric acid. So we can also get this nitrates just by dissolving the salts of carbonates in dilute nitric acid. Magnesium nitrate crystallizes with 6 molecules of water, as beryllium nitrate crystallizes with anhydrous salt. As we said, beryllium will not have the hydrated salt. So it is exception for, barium nitrate will not have the water molecules. As down the group size increases, it is not easy to form the hydrates. So barium nitrate crystallizes without having the hydrated molecule. This shows a decreasing tendency to form hydrates with increasing size and decreasing hydration enthalpy. Obviously, yes, as down the group the size increases, hydration enthalpy also decreases, so it cannot easily hold the hydration or water molecules. All of them decompose on heating to give oxide like lithium nitrate. If we see here, the nitrates will react or decompose to give their oxide, nitrogen dioxide and oxygen. Now, anomalous behavior of beryllium. We know that beryllium is the first element of the second group element. It is having a smaller size and effective nuclear charge is also high compared to other elements, right? So what happens here, as the effective nuclear charge and the size matters, it has some difference with the other elements of the same group. So that anomalous behavior we'll study now. Beryllium shows anomalous behavior, and it is having the diagonal relationship with aluminium, where aluminium is the 13th group element. So second group element is having the similarity with 13th group element, and this beryllium has exceptionally small atomic and ionic size, and that does not compare well with the other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent. The thing what you need to understand in anomalous behavior is that it does exhibit the anomalous behavior, one thing. The second one is that it has a diagonal relationship with aluminium, which is the 13th group element. And why it is happening like that? Why? Because it is having a smaller size. What size? Atomic size as well as ionic size is very small compared to the other members of the same group, and they high ionization enthalpy is due to the smaller size, and also due to that ionization enthalpy and smaller size, it forms the compound which is covalent in nature. So since it is covalent, all other elements will form ionic compound. It is a bit differ from other elements of the same group. It doesn't exhibit the coordination number more than 4, as its valence shell does not contain d orbital. I'll just tell you, as we know beryllium, it is having 4 as the atomic number. So if I take the 4 as atomic number, what happens? First shell, if this is the nucleus, will be having the first shell with 2 electrons and second shell with 2 electrons. Right. So how many shells are there? First shell will have only s orbital. Second shell will have s and only p orbital. Whereas third shell will have s, p and d orbital. Right. So it moves on. Now we are in this group where second orbit will have only s and p orbitals. So we have only s and p orbital. So what happens here? One s is having one suborbital, where p will have 3 suborbitals. So how many suborbitals? 1, 2, 3 and 4. So how many coordinate bonds it can form? Maximum to 4. It cannot form more than 4 coordinate bonds. Whereas if I consider this third one, what happens? We have S and P, that is S and P. With this we also have d orbital which has 5 suborbital, that means 4 plus 5, it will be having nearly 9. Getting that point? So what happens? Other elements, the first beryllium, magnesium, right? Then till calcium, strontium, barium. What happens down the group? Here it will be having only 2 orbits. Here 3, 4, 5, 6, 7. So down the group what happens? They will have d orbital, and this d orbital in the valence shell will make them to form more coordinate number or coordinate bonds. So this beryllium cannot form more than 4 valency or covalent number or coordination number. The remaining members of the group can have coordination number of 6, making the use of d orbitals. You can just say why beryllium cannot form the more than 4 coordination number, because it doesn't have d orbital in second orbit, where other members will have d orbitals in their valence shell. The oxides and hydroxides of beryllium are amphoteric in nature. This is a separate, like it is different from other elements. All other elements will be basic in nature, only beryllium will be different. So these are the points which make beryllium different from the other group. Now diagonal relationship between beryllium and aluminium. So they both are ionic radius, like their both ionic radius will be very less, that is 31 picometer. Whereas if you see the charge to radius ratio, if you see, it is very smaller and it is almost similar to that of aluminium ion. Beryllium resembles aluminium in some ways. What are these similar properties of the alkali, like aluminium and the beryllium, is that they are not readily attracted by acids as they are amphoteric in nature, because the presence of oxide film on the surface of the metal. And this beryllium hydroxide dissolves in excess of alkali to give the berylate ion, and even the aluminium has the similar property. It also dissolves in excuse me, it also dissolves in hydroxides or the alkali and gives you the aluminate ion. So the beryllium gives you berylate ion and aluminium gives you aluminate ion, and they react with alkali to give these ions. So they have the similar properties. Even aluminium is also forming a oxide which is amphoteric in nature. The chlorides of both beryllium and aluminium form the bridge. As we shown, what happens? You will get a bridge like, right? The chlorine can be attracted by both the beryllium atoms. Similarly, what happens? Aluminium will also have the chlorine bridge in the vapor phase. So it is soluble in organic solvents because they are more covalent in nature than that of having the ionic nature. So we can say they are also soluble in strong Lewis acids, and they are used in Friedel-Crafts catalysis. So Friedel-Crafts reaction comes under hydrocarbons. We can just study in the organic chemistry. Later when you get to know about this, there will be using aluminium chloride and also beryllium chloride as a Friedel-Crafts catalyst. Beryllium and aluminium ions have strong tendency to form the complexes. So they form the complexes. You can know only beryllium will have +2 as a charge oxidation number, but it can form the bond with fluorine with having the negative charge on them, and this again forms the attract the positively charged particle and make the complex. So they can easily form the complex. They have the tendency to form complexes. So these are the things which we studied about the second group elements. Next, in coming sessions, we'll discuss about some of the compounds of calcium. So hope you enjoyed this class, students. If you have been understood, that's well and good. If you have some of the doubts, we are here to help you out. We always welcome you. If you have any doubts, you can get back to us for clarification. Thanks for watching Vista's Learning.